this lecture, we will first understand the concept of linear independence to subsequently understand the concept of dimension. Linear independence is formally defined as follows. A set of vectors v1, v2 to vn is linearly independent if the solution to this equation, that is alpha 1 multiplied by v1 plus alpha 2 multiplied by v2 and so on, is equal to 0, has the solution alpha 1 is equal to alpha 2 is equal to 0. That is the trivial solution. This set of vectors is linearly independent if and only if it has the trivial solution. Otherwise, the set is not linearly independent. If a set of vectors is linearly independent, we cannot represent one vector in terms of the other vectors. Conversely, if a set of vectors is linearly dependent, then at least one can be written in terms of the other vectors. Here are some examples of linearly independent vectors. You can find more examples on the web. To find out whether a set of vectors is linearly independent or not, you put them as column vectors in a matrix and find its determinant. If its determinant is non-zero, they are linearly independent. Here is another example of three vectors. Now, these three vectors are clearly linearly independent. One vector is 1, 0, 0, the second one is 0, 1, 0, and the third one is 0, 0, 1. These are also unit vectors and are clearly orthogonal to each other. You can imagine that what values of alpha 1, alpha 2, and alpha 3 would make the sum of these vectors equal to 0. The only possible way is that alpha 1, alpha 2, and alpha 3 should be equal to 0, and only then will their linear combination be equal to 0. Hence, these three vectors are linearly independent. This slide simply expands what I have just explained. We want to add these three vectors in these proportions such that the resultant is 0. The only way we can achieve this is that these proportions themselves are 0. Hence, these three vectors are linearly independent. Dimension. In a vector space, the maximum number of linearly independent vectors is fixed, and this is called the dimension of that space. In an n-dimensional space, any set of n linearly independent vectors form a basis for that space. Given a basis v1, v2 up to vn, any vector w can be written as a linear combination of these basis vectors, where the coefficients alpha I are unique and are called the representation of w. In the example before, the dimension of the space is 3. Let's look at this vector, where w values are 10.5, 21.3, and 0.9. This can be written as w is equal to 10.5 v1, 21.3 v2, plus 0.9 v3. And the coefficients alpha 1 is equal to 10.5, alpha 2 is equal to 21.3, and alpha 3 is equal to 0.9 are unique. This is the only set of alpha values that can represent this vector.